Okay, dear colleagues, it's 10 a.m., 10 p.m., 10 a.m. in the morning in Moscow, and I think it's 4 p.m. in Japan. I think so. And
Yes,
I'm
yes.
happy to start our today's session. So the first invited speaker of today is Professor Akio Kawauchi from Osaka, and he will tell us about the Kervaire conjecture on weights of groups. Let's welcome.
Okay, thank you. Yes, I'll speak about the content of this paper, referred as K0. It's a Kervaire conjecture on weight of group via fundamental group of ribbon sphering. So its main tool is in surface knot in four space. Okay. Sorry. Okay, so let G be a group, and I element of G, and NW1 from W1 to Wn is the smallest normal subgroup in G generated by the element Wi. So it's called the normal closure of element Wi. Weight system of G is a system of element Wi such that the normal closure of Wi is equal to G. Okay, and the weight of group G is the least cardinal number of a weight system of G written by Wg. Okay, if G is not non-trivial group, of course, Wg is positive. The rank of G is the least number Rg of generators of G, okay, written Rg. So the difference of Rg minus Wg is greater than or equal to 0. And in general, taken as a large number. For example, take a polygonal knot K in the 3-sphere S3. Let G be the group of K, or not K, okay? The fundamental, G be the fundamental group of not K, okay? Then G is infinite cyclic group, then G equal 1, R equal 1, generator 1, okay? And Rg equal 2 if K is a trophile knot, and Rg equal N if K is a connect sum of the n minus each n minus 1 copies of the trophile knot. On the other hand, Wg equal 1, weight 1, okay, for every knot, K. Because normal closure of one element, meridian element, or normal closure equal to G, okay. Let G star Z be the free product of a group G and the infinite cyclic group Z. Kervaire conjecture is the W of the weight of the free product G and Z. Okay, it's greater than 1 for every non-trivial group G. Here is a paper of their paper, okay, written of this conjecture paper, but they don't never conjecture, but later most people say that it's a conjecture. Okay. Some partial confirmation of these conjectures known. For example, the following result is used in this talk. It's a Krachko theorem. It's a weight of every non-trivial Tojo-free group G and the infinite cyclic group Z is greater than 1. Okay? The paper is here, and I think it's some other persons, there is independent proof there is also. So not exterior, it's a compact 3 manifold. So it's for a tubular neighbor, complement of a tubular neighbor to NK over polygonal knot K in 3 sphere, 3. Okay, it's a not exterior. So, and let F be a compact connected orientable non-separating surface in E, such that properness, okay, E boundary, E union intersection equal to the boundary F, okay, it's so proper surface. And the EF is just directing the normal line boundary F1 cross I, okay, from E. It's a closure. It's a it's a right EF. Okay, so EF plus is EF union and the cone of F cross boundary I. It means so I is a -1 to 1 interval. So its boundary I means -1 and I union two point. Okay, F cross 2 point removed. It's a cone. Okay, joining a cone. It's I denote EF plus. Okay. So this EF plus may be considered from E by shrinking the normal line boundary E cross I into the vertex V with the same one. So Gonzalez Acuma and Ramirez showed the following theorem. Conjecture, Kervaire conjecture is equivalent to the following conjecture. It's a conjecture Z. It's a fundamental group of EF plus, okay, for every not exterior E, and every compact connected orientable non-separating surface F in F. It's a so proper surface, okay, non-separating proper surface. It's a so EF plus, it's an infinite cyclic group. It's okay. It's a conjecture Z. For conjecture Z, some investigations are done by not theoretical approach. W. Munoz, it's a so it's a such a surface. If it may have a boundary, it does not connect it in general. Okay, it's a so this problem makes hard problem. It's not so and some pretzel note case is they proved this conjecture that is confirmed. So today's main theorem is a conjecture Z is true, and the corollary is a Kervaire conjecture is true. So outline of how to prove its main theorem. Okay, it's a EF plus plus. It's just written F EF union. For each point, F cross 1 and F cross -1, each point is taking a cone. So 2 cone point, there is V plus and V minus. Then EF plus is homotopy equivalent to the bouquet of EF plus plus and S1. Okay. So the fundamental group EF plus is isomorphic to the free product of pi 1 of the fundamental group EF plus plus and Z. Okay. So So the fundamental group of EF plus is infinite cyclic if and only if the fundamental group of EF plus plus is trivial. Okay. So conjecture Z is equivalent to the claim that the fundamental group of EF plus plus is trivial. So classical theorem says if G is Tojo free and weight of G star Z, okay, E is one, weight one, then G must be a trivial group. Now the E pi one of weight of pi one or EF plus equal E pi one of EF plus plus star Z weight equal one. Why it's a because this group of pi one EF plus it's a quotient group of pi one EF and this is a not group, so weight one, okay, of not so quotient group is also weight one, so this lemma is proved. So lemma two, so this is a main point, main part. It's a fundamental group of EF plus is Tojo free. Okay. This lemma is explained later. And then pi one of EF plus plus is Tojo free and pi one is Tojo free. Well, what mean? Yes, so classical theorem. I mean, Tojo free. So the classical theorem it's trivial. So this is an infinite cyclic group. Okay, that is a conjecture that is confirmed affirmatively. Okay. So the how to prove the lemma two? Okay? So plan of the proof it's a construct of finite contractible two complex, which contains as a subcomplex two complex P, which is a homotopy equivalent to the three complex EF plus homotopy equivalent. Such a two complex is a construct. Okay, and such a complex is a subcomplex of some finite contractible two complex Q. Okay, so every subcomplex of finite contractible two complex is aspherical. Okay, I use this result. Okay, this result is in this preprint. Okay, and since a fundamental group of a connected aspherical complex is Tojo free, so it is concluded by one, the E pi one EF plus is Tojo free. So proof of lemma two using theorem K1. Okay. So it's just a careful collapse to it's first to collapse E into a triangulated graph by using that F is a bounded surface, so collapse to one complex. Okay, enlarge on the fiber I over normal line bundle is I is some more bigger line bundle J. Okay. F cross J, okay? It's some enlarge of the line bundle. and the fiber complex of JC is a consists of two intervals, okay? And EF plus is so some bigger, yeah, some smaller, okay? E minus F cross J, it's so, and collapse to F cross JC into a J gamma cross JC, okay? It's a F collapse to gamma, okay, graph. And gamma cross JC triangulate, maybe something careful collapsing, but anyway, collapsing is given. And okay, EF plus is any collapse to a finite complex P minus, and the collapse union of gamma cross JC and the cone part is, this is a two complex, okay? Collapsed from EF minus, okay? And these two complex is a subcomplex of three-dimensional complex Q, cone V, okay, four cone, okay, taking. And since every two complex of gamma cross JC contains at most one simplex of gamma, maybe some such a delicate things, but anyway, collapsing, okay. Anyway, collapse to okay, okay. P is homotopy equivalent to EF plus and EF plus, and C is a contractible two complex. C is what is a C? C is a okay. So three complex Q is collapsed to it's two complex C. Okay, it's so three complex is contractible. So this is a contractible complex. C is contractible complex. So C is complex, and P is a subcomplex of so the fundamental group of P, it's a homotopy equivalent to EF plus. So this is Tojo free by theorem K1. So the main point is a proof of theorem K1. Every subcomplex of a finite contractible two complex is aspherical. I tried that proof with this paper, okay, K1. So this is the main point. So just some terminology. An S2 link is a collection K of finitely many disjoint two spheres smoothly embedded in the four sphere, S4. An S2 link K is trivial if the component Ki of K bounds disjoint three balls smoothly embedded in S4. An S2 link K is, this is a new concept. It's an S2 link K in S4 is a free S2 link if the fundamental group of K is a free group, but not necessarily meridian based. Okay, meridian basis free does not need. Okay, anyway, it's a free group of the fundamental group of K is a free group. In that case, I call a free S2 link. An S2 link K in S4 is a ribbon S2 link of R component. This is a standard terminology. If K is equivalent to an S2 link obtained from many trivial S2 link, for example, of here, Q plus R component in S4. So standardly, trivial S2 component, S2 link is given. And surgery, 100 surgery, attaching 100 is so S1 cross D2, okay? 100, embedded 100. Q embedded 100 attached to here. In general, it's make a higher genus surface, but nowadays it's only a two sphere only. So different two component of trivial two link and 100 is make S2 component. Such a case is considered. It's a ribbon S2 link of R component. Okay, and ribbon this concept is also very important. Ribbon disk link of R component. It's needed. It's a proper disk system union of the maybe it's a disk system of the union of di. It's from I equal 1 to q plus r di union the band of maybe here is a band, okay? Disk and band bj. Bj is a BJ, this DI is a proper trivial proper disk in four disk D4. Okay, trivial. Okay, disk standard disk in proper standard disk in D4 under the spanning band, but it's a disjoint band in the boundary. Okay, in the boundary three sphere. So boundary is just usually called a ribbon link. Okay, boundary is in three sphere. But now this is improper forms improper disk system. But interior is pushed into the interior of D4. Okay, so interior push of this one. It's a so proper disk system is obtained in the four disk. It's called the ribbon disk link, okay, of R component here. And it is a very natural thing. It's every ribbon S2 link L in S4 is a double of a ribbon disk link LD in D4. Okay, by construction. Okay, it's just a standard okay, disk link and is so symmetric position there is in S4. Okay, it's a ribbon S2 link. And alpha B is orientation reversing reflection of the ribbon S2 link. So S4L pair. Okay, changing one copy of copy D4LD into the other copy. It's written denoted minus D4 minus LD. Okay. So ribbon group lemma I call here the inclusion of D4LD into S4L induces isomorphism, okay, or in fundamental group, because this is just a general position, okay, and the reflection is used, okay. And the spine lemma, this is also a folklore result. It's an exterior of ribbon disk link LD, exterior with R component in D4. It has a handle decomposition of 1, 0 handle and Q plus R, R1 handles and Q2 handles. Where come from? Well, it's a Q plus R. 100 means a trivial disk system, okay? Q plus R. And Q200 is a band, okay? Band is a first boundary and interior push, okay? is obtained. So in this case, this is a two-hand makes, okay. So anyway, so the exterior of LD has a spine of finite connected two complex. So this is a very important point. It's every ribbon S2 link K in S4 for every ribbon S2 link K in S4, there is a ribbon free ribbon S2 link L in S4 with K sublink. How to get? It's just by constant surgery trace. It's so mean in S4. It's a trivial link. Okay, trivial many kind of R plus Q component of trivial S2 in S4 first consider, and such a trivial link cross I, okay, line line interval, okay, line bundle considering. So all cross I, okay, and the one side it's attaching 100 H, okay. So we'll give this is a K component, okay, three manifold bounded by K union minus O, okay. In this case, O dash be a sublink of O with N minus K components of O obtained by removing one component of O used for each component of K. For some K component, K, okay, ribbon K is, in this case, there is some trivial component is made from fusion, but one component drop out, okay? In this case, the fundamental group is just, so it's O dash, it's and union, in this case, union of K union O dash, okay? So in this case, it's from fundamental group S4 minus W, it's isomorphic to this one, the fundamental group of K union O dash, okay? And also fundamental group isomorphic to S4 minus W, fundamental group of S4 minus W is a fundamental group of O. O is a trivial link. So this is a free group. So this means a free ribbon extension lemma. Sorry. Next is a free S2 link surgery lemma. This is maybe just to explain first the result. Let L be a free S2 link in S4. With the fundamental group is identified with the free group X1 to X, from with basis X1 from X1 to Xn, okay? And Y the 4D manifold obtained from S4 by surgery along L. Then the fundamental group is just isomorphic to pi 1 Y. Okay, so this is a free group, okay? And second, so and the second homology is trivial. So this means Y is diffeomorphic to the closed 4D handle body. It's a YS. I denoted by YS. It's a connect sum of S4 and the N copies of S1 cross S3. Okay, I call the closed 4D handle body by a diffeomorphism sending the basis Ki to the standard S1 cross I, okay, standard loop, okay. Maybe some best loop should be, okay. And the third is a meridian basis W1 from W1 to Wn over L. It is in S4 is a normal generator system of the fundamental group of Y, okay. So first and third is very obvious. Okay. And the second is a hardest point, but it's so using the big machine of smooth unlocking conjecture for S-link of these papers soon be shown here, and the smooth 4D Poincare conjecture K5. It's a preprint is here. It's a K2 to K4 is already published, and K5 is soon be published now. Okay. Okay. So such a
Excuse me, can you please remind the smooth unlocking conjecture?
Smooth unlocking conjecture means free fundamental group with meridian basis. In that case, S2 link is trivial. Trivial means a bound mutually disjoint three balls. Okay.
Okay.
It's proved of K2 and K3. And so link case is so K4. Okay. So K2, K3, K4 is some such a unlocking conjecture of S link is proved. And K5 is some smooth Poincare conjecture. By a similar consideration, maybe very close result. And it's by similar consideration we have close to 4D handle body lemma, maybe already observed, but why be a closed connected oriented for 4D manifold such that the fundamental group is a free group and the second homology is trivial, then Y is diffeomorphic to the closed 4D handle body YS. By a diffeomorphism, sending the given free basis to the canonical basis of YS means S1 cross some one, okay? Okay, some canonical basis of YS. So the second is the balanced presentation lemma. This is a self-contained, but in K. Yes, in K first, this paper is proved. It's for any group, for any given group presentation x1 to from x1 to xn generator and the relators are from R1 to Rn. Okay, of the trivial group. There is a free ribbon S2 link L of n component in S4 such that the fundamental group of L is identified with a free group from x1 to xn basis, and the relators are from R1 to Rn form a meridian system of L in S4. And recently, I aided of this lemma. It's a free ribbon disk exterior lemma. It's so explain is makes easier. So I use of this lemma. Let LD be the disk link over free ribbon S2 link L in the 4 disk. Okay, D4. Then the exterior ELD is diffeomorphic to the 4D handle body. 4D handle body means a four disk D4 connect sum, the boundary connect sum of the S1 cross D3, n copies of S1 cross D3, okay, boundary connect sum. It's I call the 4D handle body. So it's proof is like that. it's a canonical homomorphism of the bound from the boundary to ELLD, okay, in fundamental group. It's an isomorphism because it is an epimorphism because of ribbon case. It's just onto, okay, epimorphism between free group of the same rank. So Hoppian property, this is an isomorphism. And why D? So why be for manifold obtained from ELD by attaching YD for the handle body along the boundary. Okay, so Y is diffeomorphic to YS by the lemma, earlier lemma. So meaning that and it's a YD in YS, it's a unique up to okay, standard base is fixed. In that case, it's unique. So ELD is diffeomorphic to YD. Connected complex is a yes, connected complex. It's understood as a cell complex obtained from a bouquet of circles. Called the one skeleton P1 or P by adding Q higher dimensional cells, okay, to P1. Okay. And connected cell complex P is aspherical if the universal covering of P is contractible. Okay, if P is connected to complex, then P is aspherical if and only if the second homotopy group is trivial. Okay. And the ribbon disk, this is one of the main point. The ribbon disk aspherical theorem. Let KD be a ribbon disk link in the four disk D4. Then the exterior EKD is aspherical. In particular, the fundamental group of KD is Tojo free. So by ribbon group lemma, the fundamental group of any ribbon S2 link in S4 is Tojo free. The asphericity of a ribbon disk knot has been conjectured by Fowey after Yanagawa and Asano, Marumoto, Yanagawa failed to prove it. Okay, this paper explains that thing. So how to get the ribbon disk aspherical theorem? By spine lemma, EKD is homotopy equivalent to a finite two complex. It's sufficient. So it's sufficient to show that the second homotopy group of EK exterior of KD is trivial. So any immersed S2 sphere in S tilde in EKD, but it's by can be taken in ELD over free ribbon disk link LD in D4 by taking the ribbon disk singularity of KD and the additional trivial proper disk system in a boundary color of the four disk. Then in this case, just a sphere is earlier given of new entry of the trivial proper disk. Okay, so this is anyway, this is a proof. So and the free ribbon disk exterior lemma, the second this is a handle body. So second homotopy group is trivial. So that S tilde is null homotopy in ELD. So it's included in EKD. So fundamental group of pi 1, pi 2 of EKD is trivial. So one full subcomplex of a cell complex P is a subcomplex PF of P, such that one skeleton of PF is equal to the one skeleton of P1, okay, one skeleton of P, okay. In this case, I call the one full subcomplex. So for every connected subcomplex PS over connected cell complex P, which is not one full, there is a one full subcomplex PF of P obtained from by adding a sub bouquet of circles in P1 to PS. Okay. Because this observation is needed, because every subcomplex is considered. So for the realization theorem of compact finite two complex, for every contractible finite two cell complex, two complex P, there is a free ribbon disk link LD in the 4 disk D4 such that the one skeleton P1 of P is a spine of the for the handle body ELD. And second is every one full two subcomplex PF of P is a spine of the exterior EFD of a ribbon disk sublink LDF of LD. Because it's a ribbon disk link or sublink is always a ribbon disk link. Okay, so this is used of such a fact. In particular, P is a spine of D 4D. Okay, so corollary to 4D realization theorem. Under observation of every connected subcomplex of every contractible finite two complex is aspherical. Okay. So how to prove for the realization theorem is a contractible connected finite two complex P is obtained from the one skeleton P1 of a bouquet of n circles with base point V by attaching two cells from E1 to En for some n. Okay. Let the fundamental group of P1, okay, is identified with the free group of X1 to from X1 to Xn. And R1 to Rn, the word of the attaching data of E1 from E1 to En to P1, okay, which normally generate the pi of the fundamental group since it is a trivial group. So balanced presentation lemma, by balanced presentation lemma, there is a free ribbon S link SL such that the fundamental group of EL is identified with with a free group with base X1 to XL. And the word system R1 to Rn is a meridian system of L. By ribbon disk group lemma, for the ribbon disk link of SL, there is an isomorphism identified with a free group with basis X1 to Xn. Okay. And with the meridian system LD sent to the word system R1 from R1 to Rn. Okay. By free ribbon disk exterior lemma, free ribbon disk exterior lemma, the exterior ELD is diffeomorphic to YD. So P1 is a spine of YD. Okay. Showing first one. Let PF be a one full two subcomplex of P obtained from P1 by attaching a two cell subsystem from EI1 to EIF with the attaching word system RI1 to from RI1 to RIF. Okay. Then the PF is a spine of the exterior of ELFD equals ELD union some meridian 200 second of meridian disks. Okay, some meridian 200 of LD of the ribbon LFD obtained from LD by forgetting the component of LD with the meridian system RI1 from RI1 to RIF. Okay, so this is a second proof. Second is proof. So further development, okay, by generalized argument of ribbon aspherical cell, I tried the white-head aspherical conjecture, full white-head aspherical conjecture. Every connected subcomplex of every aspherical 2 complex is aspherical. Its original paper is here, this W, okay? This paper, and my paper is in K6, okay? But about this, I don't know the exact proof, but in the internet, I knew the following preprint confirming the conjecture by purely group theoretic method. It passed answer to the white-head aspherical question. Okay, it's my. Okay, thank you for attention. My talk is finished.
Okay, thank you very much, Kawauchi-san. So are there any questions or comments? Is there anything on the chat? Okay, please ask your questions, remarks or comments. So we have heard so many things relating group theory, 2-dimensional knots, 4 manifolds, and whatever else we have on low-dimensional topology and combinatorial group theory. Well, I think it would be great if we organize a meeting, maybe with Anton Klitschko, a seminar, maybe with Anton Klitschko, maybe with specialists on 2 knots, maybe with specialists on 4D topology. You are warm-heartedly invited to give talks at other seminars, and yeah, I really enjoyed this talk.
Thank you very much.
Okay. Okay, any questions still? If it's not the case, so let's make a small break and we will resume at 11 Moscow time.
Okay.
Thank you.